So hello everyone, welcome back to yet another video of Axiomatic Thermodynamics, and today's video is going to be about a very important process that's called the Carnot process. We talked about it when we talked about the phase diagrams and cyclic processes, that this is going to play a very important role for us because this is also where the concept of entropy was first seen as a pattern. Right, and it is also very important because this is like through this process we were actually able to define the efficiency of an ideal machine, and this was very instrumental obviously during the era of the Industrial Revolution. Right, so we can begin firstly by doing a short recap. We already saw that the Carnot process has isothermic and adiabatic processes which are involved, and it is after all a cyclic process. Hence it is also it will actually also be a reversible process. It was devised in 1824 by the French physicist and military engineer Nicolas Sadi Carnot. You can see his picture. It is a picture taken from Wikimedia. And it was, again, as I said before, it was used to motivate the idea of an idealized machine. It is till date the mathematical definition of the maximum that a machine can actually give as an output for work. Right, and as I said also before in the beginning, that it was a stepping stone to begin with the theory of entropy for yet another great scientist, Clausius. We are going to also come back to that when we talk about the second law of thermodynamics. Right, so we can begin by first seeing the process in itself. We already saw the phase diagram before. We have the P on the y-axis and the volume on the x-axis, P as in for pressure. And we saw it before that when we have isothermic and adiabatic processes, we get a graph like this, which is basically for the reversible process of Carnot. First, let us identify some of the features of this PV diagram. We can see that these black lines, they denote basically the isothermic processes. You can see that the volume as well as the pressure changes, and however the temperature stays constant, which is pretty much understandable from a normal point of intuition. While the red lines, they show the adiabatic processes. So there is basically no energy in the form of heat that is being transferred into the system or out of the system. Right. We also see, since these processes, the black ones are isothermic, they have obviously constant temperature at the 2 points, and there are 4 points, 1, 2, 3, and 4. These are the 4 points which define the closed area that is here, which basically also defines the output work out of the Carnot process. Right. We can obviously then move forward. I have a short recap of some things which are necessary to obviously also recap and also look a bit further into, so that we can start to analyze the Carnot process. Firstly, we know from the theory of ideal gases that the kinetic energy is basically when you have an ideal gas, you separate energy according to the degrees of freedom, which is F. And in each degree of freedom, you basically assign an energy unit of half times the Boltzmann constant, which is Kb, and times the temperature. This obviously comes again from the equipartition law of energy in thermodynamics, and this can then also be changed into this form of F divided by 2 RT. Again, as a short recap, for a monoatomic gas, for only one for gases with only one atom, like it doesn't obviously follow a molecule, form a molecule, then the F would be 3. Right. So we know now that the inner energy, we also talked about it in previous videos, the inner energy is basically the sum of all microscopic kinetic and potential energies. We are talking right now of an ideal gas, so we would mostly go through the kinetic energies. And if we have n number of particles, then it would just be multiplied with the average kinetic energy of each particle. And thereby we have a form like this, which would be obviously important for us. And then if, like on the left side, we have the kinetic energy, we had the kinetic energy, and then we got the inner energy or the internal energy. And on the right side, we have T, the temperature. So obviously, if we change the left side, we also change the right side. And we know from our previous video that this is CV, which is again basically the specific heat at constant volume. Right. Another reminder that for adiabatic processes, we also defined this formula here, which is with the factor of kappa, which is also constant. And we will also see sometime later when we talk more about the adiabatic processes that there is also another equation that holds for adiabatic processes, and that is that T times V to the power gamma minus 1 is also constant, whereby gamma is then a ratio of Cp divided by Cv. Right. I have made a shorter diagram of the entire Carnot process here, and then I go through it step by step. Right, we already looked at the entire plot for Carnot process, and now let's analyze again, as I said, step by step. So let's first move from 1 to 2, from points 1 to 2, and as we see, since it is red, this is an adiabatic process, and as we know from adiabatic processes that there will not be any kind of heat energy exchange. So the given work that will be done will obviously be done as the n times the specific heat at constant volume times the change of temperature. This is obviously just like this here, formula that we obviously saw before, and it will be greater than 0 because the volume is basically decreasing here in this part of the diagram, and you can see because it moves from 1 to 2, so there is a decrease of volume, and thereby the change of work is then positive, because we know that work is defined as minus P dV. So any kind of negative change of volume will actually make the W positive. Right. So then we go from step 2 to 3, and this is a black line in between, so it has to be an isothermic process. And as we know, isothermic processes, the internal energy change is basically 0. So the change of work is basically the change of heat energy that is again given to the system or taken out of the system. And from a previous video, we also know that in an isothermic process, the work done is defined as this, which obviously is less than 0 because the temperature is positive. These are again constants which are also positive, and in no way will this natural logarithm also be negative. So it is very much understandable that this entire thing will be negative. And also just from an intuition point of view, we see that the volume is increasing on this side of the plot. Then we move from steps 3 to 4. We can again also see that the temperature is constant in the previous process. Now from 3 to 4, obviously the temperature does change, and it is an adiabatic process. So in that case, again, the work done will be defined as this. Then now it moves back from position 4 to 1, and this will be an isothermic process. And in an isothermic process, the work done is again minus the change of heat energy. And it comes obviously in this time as a different temperature, T1, and different volumes V1 and V4. Again, this is positive because the change of volume is negative. Right, so we have these 4 values of work that we'll now be using to find out the entire work that is going on in this part of the plot. So again, because T3 is equal to T2 and T4 is equal to T1, we'll reduce all the terms to T1 and T2 so we can see them better. So basically I'm adding all them up now, all these terms that we saw before, and we see that this term cancels with this term, then this term will cancel with this term. So basically what I understand now is that this 2 complete terms will be gone, and we are then left with this one and this one, which we also write here. So this is basically the work that is done within the shaded region. It is basically the area under the curve in this plot. And as we also saw in adiabatic processes, this relation holds. Hence, out with some nice mathematical tricks, which is basically nothing but just small changes in fractions, we see that this ratio is also equal to this ratio. So we can obviously use this relation here in order to get a different relation out of it. So we can obviously put minus nr by how I see it, T2 minus T1 times when this is basically natural logarithm of V1 divided by V4, and here V3 is equal to the inverse of it. So basically we have a minus here also. Right, and then we basically keep the natural logarithm of V3 divided by V1, V2, sorry. So obviously this is also another way of writing the work that we get out of the entire Carnot process. There's also an interesting pattern that we see here. If we divide the 2 heat energy exchanges that we see between 2 and 3 and 4 and 1, and we divide these 2 explicitly, then we also find that it just equals minus T2 divided by T1. So it's basically that the change of heat is then proportional to the temperature. Right, as we know from previous videos, Q is not really a state variable, because again we do not see the ends of it, we do not see how it changes. It's basically a very, very small amount of heat energy that's given into the system, but temperature is a state variable, we see its change. So now we have a problem. We have not a state variable, state parameter on the left side and a state parameter on the right. So we see a very nice pattern here where we see that if we change sides for T2 on this side and this one comes here, then we see that we get a term of something like this, where we have the change of heat divided by temperature. And very interestingly, this term stays constant. This is conserved in the entire Carnot process. Why it is interesting, we will be coming to it later on, but understand it in a way that this was the start point for, this was basically the motivation for Clausius to develop the idea of entropy. But we will be coming back to that soon, in surely when we talk about the second law of thermodynamics. Right, another very important thing that is done using the Carnot process is the definition of efficiency. It's basically how much, if we write generally efficiency with the Greek alphabet eta. It tells you basically how much work you get out, as compared to how much heat energy you supply to the system, to the process. And here, if you see in our Carnot process, the amount of work that we get is basically this. While the amount of heat that we actually give into the system, we will be seeing that it is actually this step around here, whereby the Q that we the heat that we actually give to it will define the amount of work that is done by the Carnot process. Right, so it's basically the work done in the process divided by the heat energy that is supplied to the system or to the process, let's say. And for an ideal Carnot process, the efficiency is 1, because you get exactly the amount of work done, which is equal to the amount of energy that you give into the machine, to the cycle. And that would obviously be a very, very nice fairy tale world, because then all the machines would do work exactly 100% efficiently, as compared to the amount of energy that we give to the system. But however, it doesn't really work in real life, so this actually only stays for ideal Carnot machines. While in real life you have an eta which is less than 1 for real machines. Right. You can of course also define, let's say if we define this efficiency, I'll write the indices C to mark the efficiency for a Carnot process. We can obviously also mark the efficiency of a pump that basically pumps out heat away from a system. And in that case, you will have to artificially give in work in the process or in the cycle in order to bring heat out of the system. So basically, how you define it would be exactly inverted the efficiency from Carnot. So it will be 1 divided by the efficiency of Carnot machines, and it will be exactly the delta Q divided by delta W. And these are in general then greater than 1 by definition. Right. So that's all about it. These parts are obviously very much more important, and the steps in general are very much important for the Carnot process. So I really hope you like the video. Please do like and share it with your friends if you find it very helpful. Comment at the bottom of the video so that I know if I have to change anything about the upcoming videos that I'm planning for. Feedback is obviously very much welcome for me. Right, so with that, we will meet again in the next video. Thank you.